one and two-way analysis of variance. I'm going to speed up now. This is about extension the two sample comparisons from early on to K samples. The way it's done, we call it analysis of variance. In this case, one-way analysis of variance, because there are just a number of groups. The one way is that the table is a one-way structure with different groups of different observations. It's called analysis of variance because that's the way we compare the means by quantifying the differences between the means by a variability, the so-called sum of squares for treatment that quantifies how different the means are in the different groups. And then we have the error variability. We can do the hypothesis testing where we compare the two in the right way, scale the right way by an F-test. And then we can do potentially post hoc comparisons of those pairwise means if we want either a pre-planned one and I use the 5% level, or if I do all of them, I would have to protect myself a bit from being too enthusiastic about finding differences. So I have to correct myself a little bit, restrict myself. Many ways this can be done. We introduced the Bonferroni correction. Really nice simple principle. If I do 10 tests, I don't use alpha in each of 10 tests. I use alpha divided by 10. There are many other methods for such protections. But anyway, this is a nice and simple one to understand. And hopefully to remember, because that's good if you can remember that one. Two-way analysis of variance, do it right away, almost the same thing. Now that is the generalization of paired t-test, right? The K-sample is the generalization of two independent sample t-tests. The two-way or the randomized block setting is the generalization of the paired t-test. Now the same persons, if persons are in play, are used in all treatment groups. That's used in clinical trials sometimes, most often not. It's used very much in human perceptual testing, like the TV data setting that I shared with you, that you let the same humans test all your products, meaning that you can correct for the differences between individuals in such an analysis, which makes it a good design whenever it's possible. So you can decompose the differences in these data into not only differences due to treatment groups, but also differences due to blocks, that is the individuals, and then the residual variation. We can put all that into our analysis of variance table. We can do the hypothesis tests about, are the TVs really the same or are they not? Are the persons, the blocks really the same or are they not? And we can do, just as before, the post hoc comparisons, t-test, Bonferroni or not, same stuff. Game. 100% now, guys. Let's not disturb you. Well, up to a bit of uncertainty, this is 100%, right? So good enough. Residual variation is the variation within the groups, remember, right? So here it's the variation. Can you see the little, this variation, this variation, this variation, this variation, this variation, this variation. These are roughly the same in those two plots, right? What's different is the between group differences is very different in these two data sets. The SSE is the same here. The SSTR is much larger here than here. The group means are much more different here than here, but the within variation, the residual error is roughly the same. These are the two variabilities in analysis of variance. Good there. One more question. Where are the p-values? 2 p-values? Small p-values, right? They're small. Did I find something? Yes. Small p-values means significant. Something is there. What's significant? The TV means are different. The assessor block means are different. Yes. Small p-values means that we reject the null of them being the same. So we could not accept that they could all have the same because we reject that strongly due to the small p-value, right? Good. And thank you for no green ones in here. A little dance for that one, yes. Hi is back in business.